All right, here we are at the midsegment theorem and coordinate proof lesson. In this lesson, we have two objectives. The first one, to discover, use, and prove the midsegment theorem. It has to do with triangles. And then the second one, we're going to learn a new proof type to write a coordinate proof. I'm going to pause right now for the celebration and applause to die down. Okay. All right, so if you look over here at your assignment, just understand that this assignment is not in your Springboard book. It is in the purple geometry book, along with some challenge problems. So let me just briefly show you where that is on my website. So if you're going to navigate here directly, you go to the geometry tab, then it is under triangle stuff 2C. And there we are at midsegments. Okay. So then I'm going to scroll down a little piece, and then you can see the link for the purple geometry textbook. Yes, voila. And then right beside it, you've got the answer key. Now, the answer key is this pre-made key. You'll have to scroll down a bit, and it doesn't start until you get to right there where it says 5-1 exercises skill practice, just so you know. All right, back to the lesson. Okay, so here is the slide for the first objective, being able to prove, discover, and use this thing that's called the midsegment theorem. And here, if you've played a little bit of video games from The Legend of Zelda, this is the Triforce, and the Triforce perfectly shows us exactly what it is that we're going to do in this lesson. Has to do with midsegments. So speaking of midsegments, this is what they are. So a midsegment of a triangle is a segment that connects the midpoints of two sides of the triangle. And any triangle is going to have three different midsegments. So if you take a look at the triangle that we have right now, we've got triangle ABC is the whole entire triangle. If I find the midpoint of AB, I'll call it M, and I connect it to the midpoint of BC, call it P. MP is one of the midsegments. It's just one of three different midsegments. Now, you don't have to graph all of them. You don't have to draw in all of them, but you can see back here on this picture of the Triforce, it does have all three of them in there. All right. And here's a couple of more pictures for you. So please take a definition down, draw yourself a little picture to go along with it in your notes. Here is the high rail crest, if I'm saying that correctly, with also the Triforce, and then there's this one. Okay. So we're going to do a little investigation. If you snatch yourself a piece of patty paper, actually you need two of them, you'd want to get it out. Otherwise, I completely get that you don't have access to that, those little pieces of patty paper. That's okay. I've put this together in such a way that you should be able to follow along and then, get the conjecture that I want you to get. So we have a piece of patty paper, and on that piece of patty paper, we're drawing a large triangle. We're going to call that thing ABC, filling that whole piece of patty paper up. And then you're going to find the midpoints of each one of those sides. The easiest way to do that on a piece of patty paper is you just crease it. You put point A on top of point B, and you make a little crease, right? And then right there is the midpoint. Then I do the same thing for point B and C. I put point B on top of point C, make a little crease, and then there's the midpoints of those two sides. I just got to do this one more time. Put A on top of C, make a little crease, and I have my third midpoint. Then I'd use my straight edge, and I'd connect each one of those. Maybe I call them M, N, and P. And there I have all three of the midsegments. And notice that it makes four different triangles. So the question here is, what's the relationship between all of those triangles? It looks like they might be the same, but let's take a look. So if I have another piece of patty paper, I could stack it on top of this one and then just copy off one of those triangles. Let's say it's A and P there. And now I'm going to take that piece of patty paper and slide it around and compare all of the little triangles in the picture. So let me slide it right up here. Looks like that triangle is congruent. Remember the definition of congruent triangles. One of them is a series of rigid motions, so you can map one on top of the other one. Okay. Let me slide it right down here. That looks like it's the same. In order to get it onto the one that's in the middle, I'll have to kind of flip it over a little bit. There we go. So it seems like all of these triangles are congruent to each other, right? So if they're all congruent to each other, the question is, what does that mean about this midsegment? Let's say this midsegment and this third side of the triangle. Well, remember that this piece was exactly congruent to this piece, which was also congruent to this piece. It seems to imply that MN, that midsegment, is half as big as that third side. And it would also work exactly the same way for all of these. So if I, let's say, whoops, this needs to be the exact same size as this piece, which is the exact same size as this piece. And again, that midsegment seems like it is half as big as that third side of the triangle. All right, that's not all though. There's one other relationship about a midsegment, not just that it's half of the length of the third side of the triangle. Let's look at corresponding parts of these congruent triangles. So for example, if I were to measure this angle right here, whoops, I need a pin out, measure this angle, it corresponds to this angle at angle A, and those two angles would be congruent to each other. Notice what position those things are in. Those look like that they are in corresponding positions, with this being our transversal. What does that mean about these two lines? It means that those two lines are parallel. Okay, so if we put both of these things together, what it seems to be is that this midsegment is half as big as the opposite side, and it also seems that it is parallel to this third side of the triangle. All right, we're going to look at this in a slightly different way on a graph grid here in the next part of this lesson, and then put it all together as one complete theorem.